Usually when we talk about like a medical diagnosis, there's this expectation of absolute precision.
Yeah, like it feels like engineering.
Exactly. You
Yeah.
break your arm, the x-ray shows that jagged white line, and the doctor just points and says, there it is.
It's binary. I mean, it's a visible, categorized problem with a very linear solution, and we like that. We're comforted by things we can just isolate and point to.
But then you step into the world of complex systems, and suddenly that x-ray machine is completely useless.
Oh, yeah,
You
totally.
can't point to the single thing that makes a system work. Like if you've ever looked up at the sky at dusk and seen thousands of starlings moving as one giant liquid entity, a murmuration. You know what I mean?
It's incredible.
It looks like a single organism directed by a hive mind. It
Right.
breathes, it folds in on itself, it reacts instantly to a hawk diving through it.
And the instinct there is to look for the CEO of the flock, right? Like the boss bird giving orders. But there isn't one. But the complexity is just an illusion masking incredibly simple, localized rules.
Which brings us to the monumental task we are undertaking today. We aren't just going to marvel at that biological system. We are going to build it from absolute scratch.
Yeah, we are.
We are going to code artificial life, digital birds known as Boids. And we're doing it using purely mathematical rules. And we're going to do it in an environment that actively fights against inefficiency.
It is a structural and mathematical tightrope walk. I mean, to recreate natural emergence inside a rigid, highly constrained computational sandbox, it's one of the ultimate tests of a programmer.
And that is exactly why I need to give a very specific, massive shout out right at the top here. Because today's deep dive is custom tailored for a group who is tackling this exact challenge. The Bussin Sigma Scholars of Edward Little High.
Oh, wow.
We see you, we know the mountain you are climbing with this project, and this entire breakdown is for you.
It is a phenomenal challenge they've taken on. They aren't just bridging biology and physics, they're doing it within the strict confines of rigorous computer science.
Right, because the canvas we're painting on here is critical. I mean, we aren't using a multi-gigabyte pre-compiled game engine like Unreal or Unity running on some dedicated graphics card.
No, if we were, you could just throw a million birds on the screen and let the hardware brute force the math.
Exactly. But we are doing a highly detailed line-by-line conceptual walkthrough of programming this in the CMU CS Academy sandbox, specifically using their CPCS mode.
The Canvas Python coding system. Or, more functionally, the Model View Controller mode. It is a beast.
It really is.
Doing this in a browser-based educational sandbox requires extreme optimization. If you write sloppy code here, your simulation won't just stutter, it will grind to a total frozen halt. By the end of this conversation, you will have a masterclass in physics simulation, algorithmic efficiency, and just incredibly strict software architecture.
So to actually succeed in this CMU environment, we have to understand the laws of the arena before we can even think about the math of the birds. Let's talk about CPCS. I know a lot of introductory Python students are used to standard persistent object graphics.
Right.
They type, circle 200, 250, and boom, there's a circle on the screen. The computer remembers it. If you want to move it, you just find that circle object and update its properties.
That is a stateful, persistent object model. It's very beginner-friendly. But the CPCS mode in CMU CS Academy throws that entirely out the window.
Completely.
It operates on a strict Model View Controller paradigm, or MVC. In this paradigm, the graphics package does not remember your shapes at all.
Wait, not at all.
Nope. The canvas is completely wiped clean, back to a blank void every single frame, typically 30 times a second.
Okay, I want to make sure I'm visualizing this MVC architecture correctly because I know it is the bedrock of everything we are going to code. I like to think of this using like a high-end restaurant kitchen analogy.
Oh, I like that.
It really helps separate these three distinct components, the model, the view, and the controller, and understand how they interact without stepping on each other's toes.
A highly disciplined Michelin star kitchen. Let's run with that. How are you mapping the components?
So first, we have the model. In the restaurant, the model is the pantry, the walk-in fridge, and the recipe book. It is where all the raw ingredients, the raw data, live. In our CMU CS Academy code, this model is initialized in a specific function called onAppStart.
App? That fits perfectly. When you define the function def onAppStart, app, you are stocking your pantry. You take this predefined app object that the CMU framework gives you and you attach your global state to it.
Right.
It already holds some default framework data, like app.width, which defaults to 400 pixels, and app.height, also 400. It holds app.steps per second, which dictates our frame rate. But crucially, this is where you will define the data structures for your Boids, the positions, the speeds.
But sticking to your analogy, the pantry doesn't cook the food, and it doesn't plate it for the customer. It just passively holds the state of the ingredient.
Exactly. It just sits there being pure data. So then we bring in the controller.
Right, the chef. The chef's job is to take the ingredients from the pantry, apply heat, chop them up, and fundamentally change their state over time, or in response to a new order ticket coming in.
In our code, the controllers are our event handlers. We have OnStep app, which the framework automatically runs 30 times a second. And we have input handlers, like on key press, app key, or on mouse press, app, mouse X, mouse Y.
So the chef is the logic engine.
Yeah. When OnStep fires, that is the chef looking at the clock, pulling the Boid data from the model, calculating all the physics and vectors, and then updating those coordinates back in the model. If a user clicks the mouse, on mouse press intercepts that input. That's the waiter handing a new ticket to the chef, and the chef updates the model accordingly, maybe adding a new Boid's starting coordinates to our lists.
Right. But this is where the strictness kicks in. The chef absolutely never carries the food out to the dining room. That is a completely separate job.
Oh, absolutely.
That falls to the view. The view is the plating, the presentation, the expediter at the front of the kitchen, making it look pretty for the customer. In the CPCS framework, the view is exclusively handled by one single function, redraw app.
And the exclusivity of redraw cannot be overstated. When redraw app is called by the framework, the canvas has already been wiped blank.
Right.
The redraw function's only job is to look at the current state of the model, to look at where app.boidx and app.boidy currently say the birds are, and draw graphical shapes on the screen to represent that data. It plates the food so the user can finally see it.
Okay, that sounds organized, but I want to push back on how rigid this actually has to be. Like, let's say I'm coding the on-mouse press controller. I click the mouse, and I want a little splash effect, like a circle, to appear right there immediately. Why can't I just write draw circle, mouse X, mouse EY10, right there inside the on-mouse press function? Why go through the whole song and dance of updating the model and waiting for the view?
Because if you attempt that, the kitchen burns down.
Wait, really?
You will trigger a fatal MVC violation runtime error. The application will crash immediately, and a giant red error message will take over your screen.
It actively stops me.
It is actively monitoring the execution stack. The CMU framework is designed to force you to learn architectural discipline. If it sees a drawing command like draw circle originating from an event handler like on mouse press, it flags a violation. The controller can never draw shapes.
Okay, what if I go the other way? What if I'm inside redraw and I'm drawing a bird and I realize, oh, I need to move it slightly to the right? Can I just add 1 to its x-coordinate while I'm drawing it to save a step?
Another MVC violation. If the framework detects that a property on the app object was mutated, if the model was changed while the redraw function was executing, it crashes.
Wow.
The view can never update the model. The plater cannot decide to throw extra salt on the steak as it leaves the kitchen. You have to maintain absolute separation of concerns.
So if I want that splash circle to appear when I click, I'm forced to use the controller dash like on mouse press, to add the coordinates to a list in the model, like app.clicks list, and then I just have to trust that the view redrawal will loop through that list and draw them on the very next frame.
Precisely. State changes drive the view, not the other way around. Decoupling logic from rendering is how professional, scalable software is built. Now, beyond the MVC rules, we have to talk about the physical constraints of the sandbox itself, because there are some very specific quirks of the CMU CS Academy environment that will drive you insane if you don't know them in advance.
Oh, right, the import quirk. Yes, we need to save the Edward Little High scholars some serious debugging headaches here.
It's a highly specific detail, but a critical one. Due to an internal compiler bug in the CMU graphics package, the statement from CorneoGraphics import must be the absolute first line of your Python file.
Literally line 1.
Literally line 1. If you want to use the math module for trigonometry or the random module to randomize your starting positions, you might naturally type import random at the top of your file out of habit before importing the graphics. If you do that, the compiler will fail.
And you get those weird errors.
You will get very strange, cryptic errors that don't make any sense. The framework import must claim the very first line of execution.
It's like the framework is extremely jealous. It demands to be loaded before anything else. And speaking of limitations, because this is a browser-based sandbox, We are somewhat trapped, aren't we? We are in a purely Python environment.
Yes, and that is a significant handicap for physics simulations. If you were building a massive flocking simulation locally on your own desktop, you would almost certainly use a library like NumPy. NumPy is technically a Python library, but under the hood, all the math operations are written in highly optimized, compiled C code.
Right.
It utilizes your processor's vector math capabilities to crunch millions of numbers virtually instantly.
It outsources the heavy lifting to C, which is much faster than Python.
Exactly. But in the CS Academy web sandbox, we are restricted to pure Python running in a browser's interpreter. No external compiled matrix acceleration libraries are allowed.
So every single check is manual.
Every single distance check, every angle adjustment, every addition and subtraction has to run through the standard Python pipeline. That means our raw computational horsepower is severely bottlenecked. We cannot brute force this.
So we are trapped in this purely Python bottleneck. We can't rely on raw speed. That means the mathematical rules governing our birds have to be incredibly lightweight and efficient. We need to introduce the ghost into the machine. How did Craig Reynolds actually solve this?
Well, Reynolds was a computer graphics researcher back in 1986. Prior to his work, if an animator wanted a flock of birds or a school of fish in a movie, they had to hand plot the path of every single animal, frame by frame.
That sounds miserable.
Or programmers would write a centralized boss algorithm that looked at the whole flock and told every individual bird exactly where to go to maintain the shape.
Like a centralized air traffic controller. Bird 1, go left. Bird 2, speed up. But if you watch early CGI that does that, it looks incredibly stiff. It looks robotic.
Because it is. Reynolds realized that nature doesn't have an air traffic controller. There is no leader bird broadcasting coordinates to the flock. The complex, fluid, macroscopic behavior of a murmuration emerges entirely from simple, localized, microscopic rules applied independently by autonomous agents.
It's the definition of emergent behavior. Stupid individual pieces, following simple, dumb rules, collectively creating something that looks like absolute genius.
Reynolds stripped the staggering complexity of flocking down to just 3 core steering heuristics. 3 mathematical pillars. If you apply these 3 forces to every bird independently on every frame, the murmuration spontaneously generates itself.
Okay, this is the core of the physics engine. Let's break down these 3 pillars. And to help visualize this, let's use an analogy that hits close to home for the scholars. Let's think about navigating the crowded hallways of Edward Little High between second and third period.
Perfect.
It's chaotic. You are a Boyd. The other students are your flockmates.
A highly dense, dynamic environment. Let's apply Pillar 1 separation.
The personal space rule. When you are walking down the hall, your primary goal is to not crash into anyone. If someone steps into your bubble, you instinctively step away.
Mathematically, this is about avoiding crowding with local flockmates. We define a tight radius around our Boyd called the protected range. If any other Boyd enters this protected range, our Boyd must generate a repulsive steering vector to push away from them.
So how does that vector actually work in the code? Is it just a flat force? Like if you are in my bubble, I push away with a force of 10?
No, because that would cause jittering. The force is weighted inversely proportional to the squared distance between them.
Inversely proportional to the square distance. Let's ground that. What does that mean in hallway terms?
It means the urgency scales exponentially. Think about it. A kid who is 5 feet away from you is in your general vicinity, but barely a blip on your radar. You might adjust your path slightly. But a kid who suddenly trips and is 1 foot away from you, literally falling into your shoulder, generates an absolutely massive, immediate reactive force from you to get out of the way. Because we square the distance in the denominator. So if they're a distance 5 away, the force is 1 divided by 25. It's a tiny fraction.
Yeah.
But if they're distance 1 away, the force is 1 divided by 1. Massive. The closer they get, the exponentially harder you push away.
Exactly. In the code, you loop through your neighbors. For anyone inside the protected range, you calculate the difference in x-coordinates and the difference in y-coordinates. You accumulate those vectors, scaling them by that square distance formula. This gives you a net closed x and closed ballity vector.
Exactly.
You then multiply that by a tunable parameter called the avoid factor to get your final separation force.
That makes perfect sense. Okay, Pillar 2 alignment, the go with the flow rule. You're in the hallway. Everyone is generally heading toward the cafeteria. If you just stop and face the lockers, you're going to get trampled. So you look at the people immediately around you, not the whole school, just the people in your visual range, and you match their speed and direction. Alignment is about steering towards the average heading and velocity of your local flockmates. For this, we look at a wider radius, the visual range. For every neighbor inside that visual range, we look at their velocity vector, how fast they are moving in the x direction and how fast in the y direction. We sum all of those up and divide by the number of neighbors.
So if half the kids around me are walking fast to the right and half are walking slow to the right, the average I calculate is medium speed to the right?
Yes, but here is the critical part of the math where people make mistakes. You don't just instantly set your velocity to that average. If you did, the birds would snap into alignment and look like synchronized robots.
Oh, that makes sense.
You calculate a steering force. You take the average velocity, subtract your current velocity, and multiply that difference by a matching factor.
Wait, why subtract your current velocity?
Because you are calculating how much you need to change. It creates a gentle, accelerating force that steers your current trajectory into alignment with the crowd over time. It represents physical momentum. You smoothly merge into traffic. You don't instantly teleport into a new speed.
Got it. Okay. Pillar 3, cohesion. They stick with your squad rule. You're in the hallway, moving with the flow, avoiding collisions, but you also want to stay near your friend group. You don't want to drift off and end up walking by yourself.
Cohesion is steering towards the local center of mass of your visible neighbors. Again, you look at everyone in your visual range, but this time you ignore their speed. You look at their actual coordinates, their x and y positions. You average all their x positions and average all their y positions.
Which gives you a single point in space, the exact center of the group around you.
The center of mass. Then, just like with alignment, you create a steering force. You take that target center point, subtract your current position, and multiply by a centering factor. This creates a gentle gravitational pull, drawing you toward the heart of the flock, preventing the group from splintering apart.
So separation pushes you away from collisions. Alignment gets you all facing the same way. Cohesion pulls you together into a tight group. It's a constant three-way tug of war.
And tying them all together requires a basic Euler physics engine. Every step of the simulation for every single Boid, we calculate these three separate vectors. Then we simply add them together. The sum of separation, alignment, and cohesion becomes our net acceleration for that frame.
Because force equals mass times acceleration, and since our digital birds all have a mass of 1, the net force just is the acceleration.
Precisely. We take that net acceleration vector and we add it to the Boid's current velocity vector. That gives us our new speed and heading. Then we add that new velocity to the Boid's current x and y coordinates to get its new position on the screen. Acceleration changes velocity, velocity changes position.
So we just keep adding the acceleration to the velocity. But wait, physics-wise, if they're constantly accelerating toward the center of the flock, won't the velocity just keep growing? Won't they eventually cross the entire screen in a single frame? Birds don't fly at Mach 10.
Exactly, which brings us to mechanical limits. Biological systems cannot accelerate infinitely. After we calculate the new velocity, we have to calculate the total speed of the Boid. We use the Pythagorean theorem, the square root of the x velocity squared plus the y velocity squared.
That gives us the magnitude of the vector, the absolute speed.
Yes. We then check that magnitude against two parameters, maximum speed, or Vmax, and minimum speed, Vmin. If the speed is greater than Vmax, we clamp it. We normalize the velocity vector, which means dividing it by its current speed to get a tiny directional arrow with a length of exactly 1, and then we multiply it by Vmax.
Ah, I see.
This perfectly preserves the direction of flight, but caps the speed to a biological limit.
And what about the minimum speed? Why do we need a Vmin?
Without a minimum speed limit, the cohesion and alignment forces can sometimes perfectly cancel each other out. If a Boid is perfectly in the center of the flock, the net force might be 0. Without Vmin, the Boids would just stop moving and settle into static, non-biological floating clusters. Forcing them to always maintain a minimum forward momentum maintains the fluid, lifelike dynamics of a real flock. A shark has to keep swimming, and a Boid has to keep flying.
Okay, so we've got the rules of the kitchen, the MVC architecture, and we have the recipes Reynolds 3 pillars of math. Now it's time to actually start building this model in CMU CS Academy. We need to define our data in OnAppStart, and immediately we hit a massive structural fork in the road. How do we store our birds? Because my instinct, coming from a modern programming background, is to use object-oriented programming.
That is the instinct of 99% of developers.
Right. I want to create a Boid class, and every bird will be an instance of that class. It'll be beautiful. Class Boid. And it has properties like self.x, self.y, self.velocityx, self.color. I could even attach methods to it, like boid.calculateForces. So in OnAppStart, I just make an empty list called app.flock, and I append 100 Boid objects to it. That is clean, readable, modular code. Why wouldn't we do that?
Wait, hold on. In a standard desktop environment running a compiled language like C++ or Java, absolutely.
Right.
But you are proposing we do that in the constrained Python browser sandbox of CMU CS Academy. It is an absolute death sentence for your frame rate.
You want me to abandon object-oriented programming? That breaks every rule of clean, readable code I've ever been taught. Won't having a bunch of detached lists be a nightmare to debug? What is so inherently wrong with objects?
To understand why OOP fails here, we have to take a deep dive into how Python manages memory under the hood. Specifically, we have to look at object overhead and the garbage collector. When you create a class instance in Python, it doesn't just neatly store a couple of floats for X and Y in contiguous memory. Every single object in Python is actually a highly complex C structure called a Pi object.
Okay, so it's a bit heavier.
It is massively heavier. It contains reference counts, type pointers, and crucially, a dictionary datched attribute to map your property names to their actual values. When you write boid.x, Python doesn't just grab a memory address. It takes the string x, hashes it, and looks it up in that object's dictionary to find the value.
I mean, dictionary lookups in Python are highly optimized. They're generally considered fast.
Yeah.
A few thousand lookups are fast, but remember the math we just discussed. For every single Boid, we have to look at every other Boid and calculate the distance between them. If we have just 100 Boids, that is 10,000 distance checks per frame. Each distance check requires looking up boida-x, boida-y, boid-bx, boid-by. That's 40,000 dictionary lookups per frame.
Wow.
At 30 frames a second, you are asking the browser's Python interpreter to perform 1.2 million dictionary lookups every single second, just to find out where the birds are.
Oh, when you scale it up like that, the micro inefficiencies compound into a brick wall.
And that's before we even talk about the garbage collector. If you use object methods that generate new temporary vector objects during the math calculations, Python allocates memory for them on the heap. Thousands of tiny objects created and destroyed every frame. Eventually, Python's garbage collector has to pause your entire simulation, scan the memory heap, and clean up those dead objects.
That's going to cause lag.
Massive visible lag spikes. Your smooth murmuration will suddenly freeze for half a second, then jump forward.
Okay, you've convinced me. The clean, readable, object-oriented code is actually bloated and slow at this specific micro level. We have to ditch it. So what is the optimization secret? If we don't use a list of objects, how do we store the data?
We shift our paradigm to data-oriented design, or DoD. We strip away the objects entirely. Instead of one list containing complex objects, we use flat lists of primitive floats. And on AppStart, you define 4 separate lists: app.boidx, app.boidx, app.boidvx equals app.boidvx, and app.boidvx equals x.
I see. So there is no bird number 5 object. Bird number 5's data is just conceptually stitched together by looking at index 5 across all 4 of those separate lists. App.boidx5 is its horizontal position, and app.boidvx5 is its horizontal speed.
Exactly. This is called a structive arrays approach, rather than an array of structs. Iterating through flat lists of primitive numbers in Python is vastly more memory efficient. The data is packed closer together in memory, which drastically improves CPU cache hits. When the CPU asks for app.boidx5, the hardware likely pulls boidx6 and boidx7 into the L1 cache at the same time. Plus, there are 0 dictionary lookups required. You just access the index.
It feels a bit old school, right? Like writing in early C. It's a bit harder to read, but you're saying the performance gains are undeniable.
In a resource-constrained sandbox, data-oriented design is the difference between a simulation that crawls at 5 frames a second and one that glides flawlessly at 30.
Okay, Edward, little high scholars, note that down in bold. Flat lists save lives, for at least frame rates. Do not use classes for your Boids. So, we have our data structured perfectly, the pantry is stocked. Now we step into the kitchen with the chef. We need to write the controller. This is our onStep function, running 30 times a second, applying Reynolds rules to our flat lists. And here is where we hit what might be the most terrifying obstacle of computer science, the O of n squared trap.
The algorithmic nightmare. It is the silent killer of physics simulations. Let's trace the logic of onStep to see why it happens. For every single Boid in the flock, we have to calculate its new steering forces. To do that, the Boid has to figure out which other Boids are inside its visual range to align with, and which are inside its protected range to separate from.
Right, it needs to know who its neighbors are before it can react to them.
But how does it find its neighbors? The naive approach, the easiest and most intuitive way to code it, is to use a nested loop. For Boid A, you loop through every single other Boid in the entire simulation, calculate the distance to them using the distance formula, and check if that distance is less than the visual range.
Okay, let's do the math on that. If I have a small flock, say 10 Boids, Boid 1 checks the other 9, Boid 2 checks the other 9. That's roughly 10 times 10, so about 100 distance checks. My phone could do that in its sleep. No big deal.
Right, 100 operations is nothing, but algorithmic complexity dictates how an algorithm scales as the data grows. A nested loop checking everything against everything else scales squarely. That's what big O notation means when we say O of n squared or order n squared. Let's say you want a really impressive cinematic murmuration. You bump your starting flock up to 500 Boids.
Okay, 500 Boids.
Okay.
500 squared, that's 250,000 distance calculations.
Per frame. And remember our frame budget. To achieve 30 frames per second, the on-step function has exactly 33 milliseconds to finish all of its math before the browser demands the next frame. You are asking the Python interpreter to perform 250,000 square roots and power functions in 33 milliseconds.
That's 7.5 million distance checks per second.
Ah.
The browser's going to catch fire, or more accurately, the tab will just freeze and a little page unresponsive pop-up will appear.
In the CMU CPCS environment, a naive pairwise search completely caps out and starts lagging horribly at about 80 Boids. You'll watch your smooth frame rate plummet to a slideshow. To simulate a massive swarm, we have to optimize the algorithm. We have to break out of the O of n squared trap.
But how? The birds physically need the distance calculation to know who is close. You can't just skip the math.
You can't skip the math for the close birds, but you can skip the math for the far birds. Strategy 1 is a classic computer science approach, spatial partitioning. Instead of checking every bird against every other bird, we divide the sky into a grid, or we use a spatial data structure like a KD tree.
A KD tree, K-dimensional tree. Conceptually, for so-callers listening, how does that work without getting too bogged down in the raw code?
Imagine dividing your 400 by 400 canvas exactly in half with a vertical line. Now you have a left box and a right box. Half the birds are on the left, half on the right. Then you divide each of those halves with a horizontal line. You keep splitting the space into smaller and smaller boxes based on where the birds are.
Okay, I'm visualizing that.
When a Boid wants to find its neighbors, it doesn't look at the whole sky. It queries the tree, essentially asking, which tiny box am I currently in? And it only calculates exact distances to the few birds inside its own box or the immediately adjacent boxes.
That makes total logical sense. If I'm a bird in the top left corner of the screen, why am I wasting CPU cycles calculating exactly how far away a bird in the bottom right corner is? I already know it's too far.
Exactly. Spatial partitioning reduces the neighbor query complexity from O of n down to O of log n. The overall algorithm drops from n squared to n log n, which scales beautifully. It is a massive optimization that can push the CMU environment to handle around 300 Boids smoothly.
That's a huge jump.
It is, however, there is a catch. Building and updating a self-balancing KD tree in pure Python from scratch, every single frame introduces its own very heavy computational overhead. Sometimes the cost of building the grid is higher than the time it saves.
So what's strategy 2? If the pure computer science data structure is too heavy, what else do we have?
Strategy 2 is my absolute favorite because it applies evolutionary biology directly to computer science. It's called Starling's Rule of 6.
Oh, I love this intersection. Tell me about this.
A few years ago, biologists and physicists were studying real flocks of starlings in Rome. They were trying to figure out how a tiny bird brain processes all that chaotic visual information so fast without crashing. They mapped the flocks using stereoscopic cameras and discovered something incredible. A bird's brain doesn't actually track every single bird in its visual range. It optimizes its flight by only tracking its topological neighbors, specifically its 6 closest neighbors.
So evolution basically solved a computational bottleneck millions of years before computer science even existed.
Exactly. The birds evolved a processing optimization. The researchers found that tracking 7 birds is too much cognitive load, causing reaction delays. Tracking 5 isn't enough data points for smooth flock cohesion. 6 is the biological magic number.
We can just steal that for our code.
We can, and we should. In our inner loop, we don't need to evaluate every bird in the visual range. We can limit our algorithm's evaluation to a static maximum per frame. We find the closest 6 Boids, and we hard stop calculating. We base our alignment and cohesion vectors solely on those 6.
Wow, that's incredibly efficient.
By placing a hard cap on the loop, we save massive compute power. And ironically, because we are using the exact limitation the real birds use, the resulting simulation actually looks more organic and lifelike than if we calculated everything perfectly.
That is just brilliant. We hack the simulation by mimicking the limitations of the biological brain. Okay, so we've solved the O of n squared trap, but there's one more massive math problem the controller has to handle in OnStep. The edges of reality. Our canvas is exactly 400 by 400 pixels. What happens when a bird flies to the edge? It can't just fly off into the void forever because we'll lose it. We need boundary conditions.
How would you solve it?
My first thought is like the classic arcade game Pac-Man. Toroidal wrapping. You go off the right side of the screen,
Yeah.
and you instantly teleport to the left side of the screen. You fly off the top, you appear at the bottom. It keeps everyone on the board indefinitely.
Toroidal geometry is mathematically continuous, which is nice. To implement it, you just use the modulo operator on the coordinates. Boid x equal boid x% app.width.
Yeah.
Extremely cheap to compute. However, it introduces a severe game-breaking flaw into our distance calculations.
Really? Why?
Think about the geometry. If a bird is at x-coordinate 395, way over on the right edge, and another bird is at x-coordinate 5, way over on the left edge, visually, on a wrapped screen, they are basically touching. They're only 10 pixels apart.
Right.
They should be applying strong separation forces to each other, but mathematically, if you just subtract their x-coordinates, 395 minus 5 is 390.
Yeah.
The computer thinks they are 390 pixels away from each other. They will completely ignore each other and crash.
Oh, I see. So to fix that, you'd have to write code that says, calculate the normal distance. But TIF, the normal distance is greater than half the screen, calculate the wrap distance around the corner instead and use that.
And right there is the fatal flaw. You just said the word IF.
Is an if statement bad? It's just basic logic.
Inside a massive, heavily executed physics loop. Yes, it is devastating. Toroidal geometry requires branching if statements to allow Boids to calculate distances around corners. To understand why that's bad, you need a quick masterclass in CPU architecture. Modern CPUs use something called a pipeline. They don't just execute one instruction at a time. They fetch the next instruction, decode the one after that, and execute the current one all simultaneously.
Like an assembly line in a factory.
Exactly. Now, what happens when the CPU hits an if statement? It doesn't know which branch of the code will be true until it does the math, but it wants to keep the assembly line moving. So it uses something called branch prediction. It guesses which way the if statement will go and starts executing that code speculatively.
Wait, the CPU guesses? And what if it guesses wrong?
If it guesses wrong, it has to throw away all that speculative work, flush the entire pipeline, and start over on the correct branch. A pipeline flush wastes dozens of clock cycles. Heavy, unpredictable branching inside an inner loop, like checking if two randomly moving birds are on opposite sides of a screen, causes constant branch mispredictions. It heavily degrades performance.
Wow.
Yeah.
I never thought about an if statement as a physical speed bump for the CPU hardware. So if Pac-Man wrapping requires too many if statements and is too slow, what is the solution for the edges?
A non-branching soft bounding force. Instead of a hard wall or a teleport, we create an invisible magnetic force field around the edges of the canvas.
How do you do that without if statements? Don't you have to say, if the bird is near the edge, push it?
No, you can do it with pure continuous math. We define a margin, say 50 pixels from the edge. We calculate how far a Boid has penetrated into that margin. We can use the built-in min and max functions in Python, which are often heavily optimized or implemented in C without traditional branching overhead. We find the penetration depth, square it, multiply it by a constant, and apply it as a steering force, pushing the bird back toward the center.
Okay, let me visualize that. If the bird just barely crosses the 50 pixel line, the penetration is tiny, say 1 pixel. 1 squared is 1. The repulsive force is tiny, it gently starts turning. But if it flies straight at the edge at high speed and gets to 10 pixels away, its penetration depth is 40. 40 squared is 1600. The force becomes massive. It acts like an exponentially stiff rubber band and violently snaps it back into the visible canvas.
Yes. The closer they get to the edge, the harder the math pushes them back. We smoothly herd them back to the center using algebraic forces, completely avoiding expensive conditional if branching. We keep the CPU pipeline flowing fast, and the birds stay on screen.
That is next-level software engineering. It's solving a hardware problem with a math solution. Okay, so the chef is finished cooking. The physics have been calculated, the boundaries enforced, the flat lists are updated with all the new X and Y coordinates. Now we transition from the controller to the view. We enter Redraw app, the canvas is wiped clean to black, and we must draw every Boid based on the current state of our flat lists.
This is the final piece of the MVC puzzle.
And as we mentioned earlier, we aren't just drawing circles here. Draw a circle is fast, but a circle has no front or back. If you draw a flock of circles, it looks like a swarm of gnats. You can't tell which way they're flying. We need to see which way the birds are pointing so we can actually witness the alignment rule working visually.
We need directionality. So we have to draw polygons, specifically polarized triangles or dart shapes, pointing exactly in the direction of flight.
But the CMU framework's draw polygon function doesn't just take a point this way command. You have to feed it the exact x and y coordinates of all 3 points of the triangle on the grid. The syntax is draw polygon, x0, y0 by 1, y1 by 2, y2. Figuring out where those 3 points are while the bird is spinning and flying sounds like an absolute trigonometry nightmare. Sines and cosines everywhere.
It's actually applied linear algebra, and it is quite elegant once you see the trick. Let's walk through it. For every Boid, we know its center position, x and y, and because we just calculated physics, we know its velocity vector, vx and vy. The velocity vector tells us exactly which way it's pointing.
Right, if vx is positive and vy is 0, it's pointing straight right.
First, we normalize the velocity vector. We divide vx and vy by the total speed of the bird. This gives us a unit vector, a tiny directional arrow with a length of exactly 1 pointing in the exact heading direction. Let's call that dxd.
Okay, we have a pure directional arrow. It's essentially a pointer.
Now, to find the tip of the bird's beak, the front vertex of the triangle, our x0, y0, we start at the Boid's center position xy, and we add our directional arrow dx, multiplied by whatever we want the length of the bird to be. Say, 10 pixels.
That makes perfect sense. Start at the center, go forward along the arrow by 10 pixels. There's 0.1. What about the back 2 corners of the wings?
To find the wings, we need to go backward from the center and then out to the sides. Going backward is easy, just subtract the directional arrow. But to go out to the sides, we need a perpendicular vector, an orthogonal vector.
Right, and here's where my brain goes straight to heavy trig. Finding a perpendicular line usually involves calculating the current angle with arctangent, adding 90 degrees, and then taking the sine and cosine of the new angle. But trig functions are notoriously slow to compute. How do we do it fast?
We use a fantastic little math trick in 2D space that completely avoids trigonometry. If your forward vector is dx, your perpendicular vector is simply dx. You swap the x and y components and make the new x component negative. That new vector points exactly 90 degrees to the left.
Wait, really? Let me visualize that. It's like taking a clock, hand pointing at 3 o'clock. The vector is 1, 0. I swap them, so it's 0, 1, and make the first one negative. Negative 0, 1, which is just 0, 1. And 0, 1 point straight up to 12 o'clock. 90 degrees counterclockwise. That is incredibly clean. No sines, no cosines, just a swap and a negative sign.
No heavy trig functions required, which, again, saves massive compute time in our inner loop. So to find the left wingtip, you start at the center, go backward along the heading vector by, say, half the length, and then add the perpendicular vector multiplied by half the width.
That's amazing.
To find the right wing, you do the exact same thing, but you subtract the perpendicular vector to go the other way.
And boom. You have your 3 absolute coordinates on the canvas, you pass them in to draw a polygon, and you have a perfect dynamic triangle. When the alignment force subtly turns the velocity vector during the math step, this linear algebra instantly updates the triangle's rotation on the screen for the very next frame.
It seamlessly and visually represents the underlying data structure. That is the essence of a perfect view function in an MVC architecture.
Okay, so we have a perfectly functioning, highly optimized flock flying around a black canvas. But right now it's just a movie. It's a closed system. The real test of an emergent system is how it handles disruption. Because the CMU sandbox is interactive, we can add controllers that let the user mess with the system.
This is where we shift from being just programmers to being researchers. We can map the on-mouse press event to add a new Boid to our flat lists at the exact coordinate of the click. The user can literally paint new birds into the sky one by one and watch the flock instantly recognize them, process their coordinates, and incorporate them via the cohesion rule.
But what if we map on the mouse move? The user moves their mouse around the canvas. We can treat the mouse cursor's x and y coordinates as a dynamic predator, a hawk sweeping through the environment.
Introducing a predator alters the fundamental mathematics of the local environment. When the predator coordinate gets too close to a Boid entering a newly defined danger zone, we program a new, high-priority repulsive force. This predator avoidance force scales incredibly fast, much faster than standard separation, and it completely overrides the standard alignment and cohesion rules.
The survival instinct kicks in. Forget the flock. Run for your life.
Exactly. When you sweep the mouse through the flock, you witness a phenomenon biologists call fission. The unified flock shatters. Subgroups scatter in opposite directions to escape the threat radius. The macroscopic entity breaks down into chaos.
It's beautiful, but it's pure panic.
But it's temporary. Because as soon as you move the mouse away and the predator danger force drops back to zero, what happens?
The baseline math takes over again. The three pillars reassert themselves. Cohesion reaches out across the gap. Alignment syncs up the stragglers.
Yes, that is fusion. The scattered subgroups find each other, merge, and heal back into a unified, flowing flock. Watching fission and fusion emerge dynamically from these basic mathematical vectors is breathtaking. It proves the incredible resilience of decentralized systems.
And it's not just introducing predators. As a programmer, or as the user, if you attach these to keystrokes like onKeyPress, we can mess with the tuning variables themselves in real time. We can alter the weights of the three rules, the avoid factor, the matching factor, and the centering factor.
And by tweaking those 3 decimal numbers, the system transitions between distinct observable biological phase states. It's analogous to changing the temperature of water and watching it go from solid ice to liquid water to gaseous steam.
Okay, what are the states? Walk me through the phases.
If you set alignment and cohesion high, but keep separation relatively low, you get a state called polarized swarming. The agents synchronize their headings tightly because they aren't worried about bumping into each other. The swarm migrates across the canvas in a unified, highly directional trajectory. This is what you see when a flock of geese is migrating south for the winter.
High order, high direction. What if we drop the alignment? They stop trying to face the same way.
If you crank cohesion very high, they desperately want to be together but make alignment extremely weak, you lose the unified direction. The Boids constantly try to get to the center of the group, but they aren't matching speeds. The physics engine resolves this conflicting math by collapsing the swarm into a rotating ring, a continuous spinning donut. Biologists call it vortex milling.
Like a bait ball of fish in the ocean when sharks are circling. They just spin in a massive, dense sphere to confuse the predator.
Precisely. The math naturally produces a bait ball without you ever programming the concept of a circle. And finally, if you turn the separation weight up too high, if a personal space rule becomes hypersensitive and overpowers cohesion, you enter the gaseous scatter state.
Everyone hates everyone else. The introvert's flock.
Cohesion is overpowered. The flock dissolves entirely. It becomes high-entropy individual chaos. The agents scatter like gas molecules filling a room, constantly bouncing away from one another. Just by changing 3 decimal values, you simulate entirely different ecological and social behaviors.
Edward Little High scholars, take a step back and look at the incredible journey you are on with this project. You start by confronting the CMU CS Academy CPCS mode. You have to submit to the absolute discipline of the model view controller architecture. You learn to separate the pantry, the chef, and the plater under threat of instant system crashes. You fight the weird compiler bugs.
And then you completely abandon object-oriented programming and flatten your data structures to outsmart Python's garbage collector.
Right. You implement Craig Round's brilliant vector math. Separation, alignment, and cohesion. You battle the exponential O of n-squared performance trap using spatial reasoning and biological hacks like the rule of 6, optimizing your inner loops.
You invent soft bounding force fields to avoid CPU branch prediction failures from if statements. You use orthogonal vectors to render polarized triangles without bogging down the system with trigonometry. And finally, you tweak the weights to summon migrating flocks, vortex bait balls, and scattering gas clouds, all interacting dynamically with a mouse-driven predator.
It is a tour de force. It is where computer science, physics, and biology intersect.
It really is.
It really is. And it leaves me with one final kind of mind-bending thought. We just spent this entire time talking about generating incredibly complex, lifelike, highly organized behavior, and we did it without a single line of code acting as a leader. There was no manager, there was no boss telling the flock what shape to make or where to go.
It was entirely decentralized. The order came from the bottom up, not the top down.
Exactly. Just 3 simple, localized, unconscious mathematical rules. Avoid crowding, match speed, stay close. And from that, beautiful self-organizing order emerged. So here's the provocative thought I want to leave you with, to mull over long after you finish coding your project.
I'm ready.
If simple localized rules can create such undeniable order in a computer simulation, how much of human society is doing the exact same thing? Think about our traffic patterns on the highway. Think about the sudden, inexplicable rise and fall of social media trends. Think about massive cultural movements. We like to think we are acting with total free will, directed by conscious leaders and rational decisions. But how much of human behavior is just an emergent murmuration, driven by us unconsciously following the exact same localized rules? Avoid crowding, match the speed of your peers, stay close to your group. Next time you're walking in a crowded hallway between classes, take a look around. You might just be a Boyd.